Hello and welcome back to Calculus 1, section 5.2 on definite integral. So the integrals that we've done so far, the ones from 4.9, were called indefinite integrals because we did not get a number as the answer for it. We got another function. They were simply antiderivatives. They were there to undo the operator of differentiation. Today we are going to take a look at a definite integral, and we're going to look at the exact area under the curve. So what have we done yesterday? Yesterday we took a function and then divided area under that function into these rectangles. Call those rectangles x0, well, the division over here for partitioning, x0, x1, x2, x3, and x4. And then decided whether we want to use left or right. So in this case, let's use left just for the sake of the example. And then computed areas of these individual four rectangles, added those, and claimed that our actual exact area is close, not the same, but it's close as the one that we approximated, right? We calculated. And then yesterday we also said that if we are to now further divide this, and now let's use, let's say, red, we would eliminate some of the error and have our answer to be better. But we had more calculations to do. We doubled the amount of calculations. Well, it's not exactly double, but about double the amount of calculations that we have to do. We can further divide this into even smaller parts. You don't have to cut it in half. You can cut it into whatever amount you want, right? So now this is even finer mesh, which in this case I cut again in half. So now instead of having 4 or 8 calculations, we have 16 calculations only for rectangles, and then plus the additional one. So everything is getting more tedious to get this thing to work. But the idea is that if you divide this so much that you actually are able to fit infinitely many of these rectangles, and those rectangles would be at that point infinitely thin, you would have a theoretical rectangle under every point of the function. Now, points are infinitely thin, so those rectangles are infinitely thin. And when those add up, they would add up to exact area. So it's very easy to actually build the formula that we have for our problem. I would urge you to look at the formula and see the way it's built and why it works the way it works, and then it will be easy afterwards to remember this. So look at this thing. We pick one of these rectangles. I don't know, just pick any one, it doesn't matter. We know that delta x is the width, and the height of that rectangle up there is your f of x n, whatever n works out to be, to calculate the height of the rectangle. So now just observe the formula. Look at the screen. What you see now is I'm going to take just the area of this one rectangle. So I'm going to say I have f of x, and I'll call it I because I need to know, which exactly one it is, and I'll deal with that later. So I have f of xi times delta x. So this over here, and I'll label this as the area of the single rectangle. So I am able to calculate area of the single rectangle by the formula we had yesterday. And I'm just using xi because that could be any rectangle. Could be x0, x1, x2, x3, x17, whatever it is. I'm just going to call it xi. And then what I'm going to do is I am going to add all other rectangles. So I'm going to start counting in 0 and go to n. Now with this, like that, this is add all rectangles that are available to us, right? So the formula part is just the area of the single rectangle. When I put this sum in front, I am adding every single one that is on the pile. And now the final step is to say, well, you know what I'm going to do? I'm going to make this to be infinitely many rectangles. And which concept would do that? I need to change that n up there into infinity. So which concept would send this to infinity? Limit. There we go. So now to end this limit, n goes to infinity. As soon, so, and for this one, I'm just going to have a green arrow, and I'll just say make n infinite. Well, make, yeah, n infinite. Also, what it means is get. So, guys, this is going to be equal to a exact area. So this is what it is. It's the exact area. So this is how you build the formula. You start from the single rectangle, and then you add all of them, and then you send the number to infinity. It's a three-stage thing. I'm going to write that the area is equal to limit as n goes to infinity, summation I goes from 0 to n of f of xi delta x. This is the exact area formula where delta x is equal to b minus a over n in our calculations. That's from the past, right? From yesterday. So these are the concepts that we have. So now let's go and figure out area under the curve for some. Let's do the linear function. So say find area under f of x equals 3x minus 5 from, and we are going to pick the interval from 3 to 7, whatever, it doesn't matter, right? Well, I could have wrote it like this, 3 to 7, like the interval, but I didn't. I spelled it out.
No sneezing.
That doesn't apply to me. All right. So let's figure all of these things out. I'm just going to draw a random partition here. This is 3. This is 7. I'm just going to put a whole bunch of these tick marks in there. And I'm just going to zoom in on one of these tick marks and call it xi. Right? It doesn't matter which one you pick. I just want to know that if this is xi, then the next tick mark is xi plus 1. and that the difference between them is delta x. So that's important. All right, so let's build our problem. So first off, I need delta x, and delta x is going to be 7 minus 3 over number of rectangles, so that's 4 over 3. So I have 4 over 3, 4 over n. There we go, much better. So it's 4 over n. Delta x is 4 over n. Now if you pick n to be 4, well then your delta x is 1. If you pick n to be 8, is 1/2. If you pick n to be 13, then it's 4/13, right? So it could be anything. You can pick any number for that. So now we have that, and then we are moving on to the next part, which is this xi. You see, xi, location of xi will depend on I, and we can figure that out with a plus I delta x. So this is actually a formula that is there for xi, because your problem always starts at a value, right? And then to move to the next location, which is x0, right? A is equal to x0. And then to move to x1 position, all you need to do is to take your a, which is x0, and add to it 1 times delta x. To get to x2, you take your a and you add 2 delta x. And to get to x3, you have a plus 3 delta x. So that's how the formula works. And you can see that this column here, that's your i's, the counter, 1, 2, 3, 4, 5, right? Because from the first point, you use delta x to get here, you use another delta x to get there, another delta x to get there, another delta x to get there. So each one of these is adding plus delta x, right? So plus delta x, and then plus delta x, and then plus delta x, and it goes like that, right? Plus delta x every single time. So because it goes plus delta x every single time, then it's just discrete. In this case over here, you get 1 times delta x, 2 times, 3 times, going on forever. So that gives us the formula up there, and I can calculate then my xi. My xi is 3 plus I times 4 over n. Now, please don't confuse this I with a complex I. This is I counter. Generally, people in Europe use J for this, for the counter. In US, it's generally used as I. And then is also used as n, but we can't use n now because n is the number of rectangles, so that will be even more confusing, right? If you had 2 lowercase n's running around and meaning different things. So let me put this here, not imaginary. I. This is counter. It's a discrete counter. So it's just a variable that can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what it is. And it goes on. So now that I have xi, I can finally compile f of xi. Now my f is given as 3xi minus 5, I believe. Yep, 3xi minus 5. So this works out to be 3 times 3 plus I times 4. Well, I can call this 4i. I times 4 over n. That's fine. Minus 5. So finally, f of xi is calculated as, when you distribute this, this is 9 plus I times 12 over n minus 5 for the total of 4 plus I 12 over n. We are still working on a setup of the problem. So let's go back and review what we have so far. We start with a problem which says find the area under the curve, which is a straight line in this case, 3x minus 5 from 3 to 7. All I did is I calculated that delta x is 4 over n. and I developed the xi, which is technically the variable of my problem, but that xi depends on the location when we are looking, so it has to have this fancy I delta x and all of that to jump from one location to another. And then we have the f of xi at the end. So it's always the same procedure, right? You figure out delta x, then you figure out xi, then you figure out f of xi. And now we can actually compile the problem. Area is equal to the limit n goes to infinity, summation I goes from 0 to n, f of xi is given as 4 plus I times 12 over n, and then your delta x is given as 4 over n. So I'll just decipher this. So this is your f of xi, and this is your delta x. So we just plugged everything in the formula. So this step was to plug everything in the formula. Once you have everything in the formula, well, you just need to compute this thing and compute the limit. You're done, right? The number you get at the end will be the area under the curve. So we go limit n goes to infinity of the summation I goes from 0 to n. And now the only thing that I can do is distribute this thing. So it's a 16 over n plus I over 48 over n squared. Now I have to put parentheses here because summation is supposed to work on both terms. All right, so now we have to deal with the summation. Here are some facts on the side. Summation can be split on plus and minus. Also, summation operates on i's, not n's. So summation operates on i's, not n's, which means that everything else is a constant and can be kicked outside. So now in this step, I can say limit n goes to infinity, and now I have a summation of 16 over n plus summation of I 48 over n squared. That's me exercising the upper rule, where I can split these into two summations because I have a plus in between those two terms. Now to exercise the second thing on the bottom, well, summation operates on i's, which means that anything that it's not an I can be kicked in front of the sum. So now I have limit n goes to infinity, and then the summation is over here we have 16 over n, summation of 1, I goes from 0 to n, plus, and so 1 stays, right? If you kick everything out, just 1 stays. So I'm adding a finite number of 1s. Well, that's easy, like 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, right? So I'm going to add that n times. And then on the other one, I have to kick 48 over n squared out, leaving I equals 0 to n of, what do I have here? I. That's that, right? So now to compute this thing, well, on the first one we have 16 over n, right? And then this entire sum over here is just n. There are formulas for this that I'm going to show you shortly. Divided by n squared, And then this part over here, maybe we do this one, we can do this one blue as well, is going to be the n plus 1 divided by 2. Now, these formulas that are converting a summation of a constant into n, and a summation of I, and then you have also summation for I squared and I cubed, those 4 formulas are in your textbook. I have, let me see if I can I? Do I have? Yes, good. I can actually find this thing now. So this will be our chapter 5, 5.2. Or maybe 5.1, I don't know. It's somewhere. Something went wrong, of course. The only thing that went wrong is me trying to do this stuff, I guess. What's wrong here? Maybe at the end of 5.1. I know it's somewhere in the book. I don't know where. Ah, there it is. So, there they are. This is page, it's impossible, 340. All right. So we had the first one on the left and the first row on the right. Those were the 2 formulas that I had. Instead of I, they're using K. So you see that summation of C, in our case was summation of 1, was Cn, so 1 times n, we only had n. On the other side, you have n plus 1 over 2, and that's exactly what I had here as n plus 1 over 2. So that's where the formulas are coming from. You just compute them, there's some Calc2 at work there and so on. Just stay tuned, more stuff is coming next semester, right? So now, guys, you just have a basic limit from your calculus chapter 2. Right, Calc 1, chapter 2. I can cancel these n's. I can cancel 48 and 2 and put over here 24. So I have limit n goes to infinity of 16 plus, and then I have a 24. I am using plus and I am not happy. Oh no, I'm happy. Okay. I have this as 24 n plus 1 over n squared. Now, if you take a look at this, this is actually n squared also on top when you multiply these two, right? It's n squared. So all this ends up being is 16 plus 24, which is 40. All right. Look at that. Don't you feel accomplished? I hope you feel accomplished, because next one is find the area under y equals 2x squared minus 1 on the interval 3 to 9. Same steps. Figure out delta x first, which is b minus a over n, so it's 6 over n. Figure out xi, which is a plus I delta x, which is 3 plus I 6 over n. Figure out f of xi, which is 2 times 3 plus I 6 over n squared minus 1. So this is where you take xi and you plug into the original function. And now you have to expand all of that and add like terms and all of that stuff. So we have 2 times, now you have 9 plus 18 times 2, 36. So I 36 over n plus I squared 36 over n squared, close parenthesis, minus 1. So f of xi is going to be 2 times 9 is 18, minus 1 is 17, plus I 72 over n, plus I squared 72 over n squared. All right, so I just want to make sure that all of this is good. 3 times 6 is 18, double that because of the formula, that's 36 over ni, good. 36 over n squared, and then the I squared when I square the last term, good. 2 times 9 is 18, minus 1 is 17. 2 times 36, 72. 2 times 36, 72, and everything else stays. Great, that's it. This is the preliminary work. You have to do these 3 things. Thing number 1, thing number 2, thing number 3. And you have to do them in this order because clearly xi is using delta x, right? And then f of xi is using xi. So this is the only order. Just like when you're driving a car, you first walk towards it, right? And then you unlock the damn thing. Then you sit. Now there is now discussion, and it shouldn't be. You should first put the seatbelt and then turn the car on. But, you know. But you can't drive the car until you get in and start it, right? So there is a sequence of events that has to be done in order for you to drive from point A to point B. So the same thing goes here. Your delta x has to be calculated first, then xi, then f of xi, and then you're done. Once you have your f of xi, you are ready to set up your limit. So limit n goes to infinity, summation I goes from 1 to n, and then we have the f of xi, all in parentheses, that's 17 plus I 72 over n plus I squared, who picked this number, 72 over n squared, times 6 over n. Again, as in a previous problem, this thing over here is your f of xi from the formula, and this thing over here is your delta x from the formula. So all we have is the formula, limit, summation, f of xi times delta x. If you already forgot, this over here is the area of a single rectangle, then this over here is the area of all rectangles that are there, and then this part over here sends the number of rectangles to infinity, which makes this infinitely small, infinitely thin. What happens when you divide 6 by infinity? You get 0, right? So you see that it's whatever the height is times infinitely thin. I told you it has to be the width of a point, and the point is infinitely thin, so you can fit the rectangle under every single point, so there is no error anywhere. Now I distribute 6 over n, split into sums on all of these pluses, and then work out the formulas, and we're done. So split, now the parenthesis has to go on outside. I goes from 1 to n, and just 17, oh no, 6 times 17. That's a 1, is that 102? Let's say it's 102. 102 over n, because 6 times 17, right? That's 60 plus 42. Yeah, it's 102. And then we have plus I. 432. This is what happens when you pick numbers like this. Plus, oh no, I'm supposed to split this. Plus another sum, I goes from 1 to n of I 400, I say 432? Thank you, over n squared, because there is n inside and then outside, so that's n squared on the next one. And then plus the third sum, I goes from 1 to n, and oh, it's the same number, 432 over n cubed as I cubed. I forgot, there's that as well. It's not I cubed, it's I squared. Hold on. N cubed, I squared. That's it. So now we are going to write the limit. N goes to infinity. And then I have, we kick all the constants outside. So we have again summation of 1, going 1 to n, plus 432 over n squared. That's a constant, because summation operates on i's, so I is all it stays inside, plus 432 over n cubed, summation of I squared, right, from 1 to n. And then we go and compute all of these. Again, we are going to have the blue formulas now, right, from last time kick in. I have 102 over n, and then the whole thing over here was just n. Then we move to plus 432 over n squared, and we know that this was n plus 1 over 2. Plus 432 divided by n cubed, and this one over here is, if I remember well, it's n minus something, n plus 1, 2n plus 1, there we go, over 6. n plus 1, 2n plus 1, everything over 6. So limit n goes to infinity, these n's die, I just have 102, plus 432 cancels with this, which is 216, n plus 1 over n squared, plus, what's this, that's 7, oh, that's divisible by 3. Okay, so what's 216 divided by 3? That's 72, right? Yep, 72, n plus 1, 2n plus 1 over n cubed. So limit applies to this. Now, please observe that the exponents are the same. If you get different exponents on n's, that you're doing something terribly wrong. So you have the order on the second term in the middle. The order is n squared over n squared, and over there you have 2n cubed over n cubed. So the numbers over here are 102 plus 216 plus 2 times 72. That's 318 plus 144 for the total of 462. Again, when you are multiplying this out, n times 2n is 2n cubed. And the limit of 2n cubed divided by n cubed, well, it's just 2, right? So 2 times 72 is 144. You will say, well, when we multiply more, right? When you multiply more, you're also going to have like maybe n over n cubed, and yeah, those all go to 0, so we don't care about them, right? We only care about the front term, because the front term is the only one that survives. The rest is, no one cares, because they're all 0. N goes to infinity. Anytime you have the denominator higher exponent than the numerator, right, everything else cancels, and at that. So this n cancel gives us 102, and yeah, there's the calculation. So the exact area under the curve is 462. Let's do something else now. Or the integral of, what was the problem? 2x squared minus 1 from 3 to 9 dx. Well, you haven't seen this before. This is just a standard integral from 4.9 with these limits 3 and 9 from the interval plugged on the integral. All right, so now we know how to integrate from 4.9, right? You took the test, and you know that you can. We know that you can integrate for the most part. So when you integrate 2x squared, you get 2x cubed over 3 minus x. And now we don't put plus c, we put this vertical line with, say, 3 and 9. And this vertical line is read as computed between 3 and 9. I haven't given you a formula for this yet, but eventually I will. So now this is, I'm going to compute this. I understand you don't know this yet, but just bear with me. So I will plug in a 9 over here. I'll have 9 cubed minus 9. Right? Oh no, that's bad. So plug in 9 first. You get 2/3 9 cubed minus 9. There we go. And then minus 2/3 3 cubed, and then plus 3. I'll explain all of this stuff. And now we compute this. All right, so I have 9 cubed. That's going to be 9 squared, so 2 times 81 times 3, because one of the 3's will cancel with 3. Minus 9, minus, why did I put squared over here? It's 3 cubed. Oh, because I already canceled in my head. So that's 2 times 9, because one of the 3 cancels, and then plus 3. So all we need to is to compute this. 3 times 81 is 243. Times 2 is 486. There we go. Minus 9 minus 18 plus 3. 486 plus 3 is 489. Minus 9 is 480. Minus 18 is 462. All right, so now we're going to do, you know, when you go to eye doctor and they say, what's better, A or B? You know, A or B kind of deal. They show you 2 things. And then you just have a headache. You can't make a decision between the 2 because you haven't been able to see for some time. So it's like all same to you. But I think that over here everything is clear, right? If the problem starts here and ends 2 pages later, and then you have a half a page calculation or a quarter page calculation in here, I think it's clear which one is better, right? So this is the same deal as computing the limits long way with difference quotient formula and computing them the easy way when you memorize all of those little rules, which is the reason why we do not compute integrals this way. Right? I mean, imagine just knowing all these formulas all the time when you're supposed to integrate something real quick, which is never, obviously. So we are going to use the antiderivative from 4.9 to compute what's called the definite integral. And the definite integral will be the one that we are focusing on, because it gives us the area under the curve. It gives us that number of 462 that we want to see at the end. And it's much quicker than the long way cranking the limit and sums and all of that stuff. So now, in that light, we are going to write that the area is equal to integral a to b of f of x dx, which is equal to the antiderivative capital F of x from a to b, where you have f of b minus f of a. And this is exactly what I did. I will be boxing the hell out of this statement here. Look at that. We put the red box, then we put the barbed wire around it, and then we... Now, this is like something that you want to tattoo on your body, because this is one of the greatest achievements of our species, figuring out this thing, which gives us most of the technology that we have today. This calculates the area under the curve, but it also calculates the accumulation. It is widely used in physics. It's used in many areas. Well, actually, all areas of human endeavor, you will find the definite integral computing something. Now, there is one thing. This comes with a disclaimer, you know, the fine print, except I'm going to write it in blood. And that is, make sure that at all times function is above x-axis. Otherwise, you are doomed. All right? So, area, and I'll put a little asterisk there, and there it is. Make sure f of x is positive on interval a, b. What that means, above x-axis. Now, this is extremely important because, well, let's just do the example immediately to show why is this important. If I calculate the integral from 0 to 2 pi for sine x dx, I'm clearly calculating the area under the curve, right? Would you agree that if I am to graph sine x from 0 to 2 pi, there is area that you can color? Is everyone okay with that? I can pick, let's say, green, and I can color the area under the curve. So area exists, right? We all see that. Bueno? All right. Now let's calculate this integral up there and see what happens. The integral of sine is negative cosine. Very good. And then we have to compute that between 0 and 2 pi. So now you have negative cosine of 2 pi minus minus gives you plus. Guys, remember that there is a minus in the formula right here. So it's upper limit minus the lower limit. I mean, f of upper limit. So antiderivative computed at upper limit and then minus. But this has a minus in front. So minus minus gives plus. And this gives me now cosine of 0. Now cosine of 2 pi is 1, which gives us negative 1 over here. Plus cosine of 0 is 1. And this calculation gives me 0. And I know that's not good because I just colored that green. You've seen it, right? So area is not 0, but the calculation tells me it's 0. So this integral doesn't give you, well, what happens here is this is symmetric. So the area over here is positive, the area over here is negative, so the net is 0. Because they just add to 0. Now, this can be fixed, right? But see, it requires the knowledge of functions. And you have to be very careful that your functions are not dipping below x-axis. So your job, not just for sine function, for all functions under the sun, is to know if they dip below x-axis, to split them and then put the absolute value on every integral that is below x-axis. That will bump. Remember the first day we did this? Yeah, because of this. The absolute value of sine x is going to bump that piece up, and then the area under this would be 4. And I say, oh yeah, that's what I covered. I colored 4 square inches or square foot or square miles. I was able to paint over that area. So now, in order for us to actually do this problem, I have to write some of the rules of definite integrals. And the first rule says that if you calculate definite integral between a and a, common sense is that the answer has to be 0 because it computes the area, and one of the dimensions is 0 because you get f of a minus f of a, right? So there's that. The next one is really cool and useful, but not until 5.5, and then obviously Calc 2, 3, and on. And this formula says that you are allowed to swap the limits of integration. So you can put the bottom limit up and upper limit to the bottom and get the same answer as long as you put the minus in front. So if you swap the limits, the integral picks up minus in front, which should be common sense because at the end, this is capital F minus f of b minus f of a. Well, if you swap them and factor out the minus, you get the same thing. And finally, the third one is the one that we need to fix our sine problem, is integral of a to b f of x dx can be integral a to c f of x dx plus integral c to b f of x dx for any c in AB. Technically, what the third rule says is you can cut your interval. Guys, that should be common sense right away. I'll draw the picture. You have some arbitrary f of x, and you're integrating between a and b. Here, cut there with c. Do you see that the area a to c plus area c to b is actually AB area, right? So you are allowed to cut anywhere between a and b, anywhere. Clearly, if you have vertical asymptotes and all kind of exotic stuff, you can't integrate to begin with. So, don't plan on doing this for integral. That's Calc 2 is addressing that kind of stuff. You're integrating 1 over x from -1 to 1. Well, there's a vertical asymptote at 0, and things don't behave nicely at the vertical asymptote. So we're going to have a whole section on what we call improper integrals, where the area leaks to infinity, and found still that some of the integrals are finite, which will be a little bit freaky, but that's how the universe works. So we are allowed to cut anywhere. So let's fix sine x problem. I know the graph for sine because I am brilliant, right? All right, so I have this. Clearly, pi is the location where where the graph goes under the x-axis. So now, my good old integral that's not a 0, that's 0. 2 pi of sine x dx is going to be integral 0 to pi, so our c is now pi, of sine x dx plus the absolute value integral pi to 2 pi sine x dx. And the reason why I have the second portion in the absolute values is because that's the negative part and I want to bump it up. So now if you integrate and compute, the life would be great. We have negative cosine x 0 to pi plus absolute value, again negative cosine x. The good thing about this when you split is you don't have to integrate two separate things. It's the same integral, just different numbers. All right, so negative cosine pi plus cosine 0 plus absolute value of negative cosine 2 pi plus cosine pi in absolute values. Negative cosine pi, so that's negative 1. Okay, good. Plus 1 plus absolute value of negative 1 plus negative 1. For those of you who don't know, cosine of pi is negative 1 because right? Cosine of pi is negative 1. So now what I have is 1 plus 1 plus absolute value of negative 1 minus 1. Well, that's 2 plus absolute value of negative 2, which is eventually 4 after all the absolute value calculations. Yay! Area under sine curve is 4. So that's what I colored. That was green, right? I can color the area. So what is necessary from algebra to survive these types of calculations? Well, clearly finding the roots of a function, right? If I have a cubic function that dips below x-axis, well, you better be able to find those roots because it's at roots that the function dips below. And then those roots become your limits of integration, right? So, say the function goes like this, whee, right? And you want to go from 0 to whatever b value is. Well, your job is to find where these roots are, and let's call these roots x1 and x2. How many separate areas do you have in the calculation? So area 0 to b. I want to say a to b, but let's say that a is 0. So how many areas do you have to consider between 0 and b? 3. 3 areas. I have the red area over here, I have the blue area over here, and I have the green area. Holy nightmare. Come on. Yay! There's it. Green area right there. How many negative areas? 1. And the color of the negative area is blue. Great. So I have my positive red integral, no need for absolute value. I mean, if you put the absolute value on each individual one, you're not going to make a mistake because absolute value of positive is still positive. Right? So if you really don't want to think at all or figure this out at all, just put absolute on each one of them, right? But we don't need it for red. So 0 to x1 of f of x dx, and then we have plus, and here comes the blue area underneath, so that's absolute value, and then we go from x1 to x2 dx, and then we finally have plus the third area is green, so that's going to be x2 to b of f of x dx, and then that calculates the area. So let me say actually area equals, right? So any time when the function dips below x-axis on the integration for that range, for that domain you have to find the absolute value of it. Why is this? How? What? The entire day, technology twilight zone over here. Good. So that's the theoretical part. So let's just solve one or two definite integrals to reinforce the knowledge of the formula which I boxed, which says when you have the integral of a function, find any antiderivative and then go f of b minus f of a. So antiderivative computed at the upper limit minus the antiderivative computed at the lower limit. Oh, no one asked yet why no plus c, and it hurts. All right, it does. That just tells me that you are not yet married to plus c, and you should be, as your exam was. Yeah. There was about, I should actually start keeping track on the amount of points, like class-wise, at least 20 points gone for the entire class. I mean, not per test, but at least 20 points gone amongst all of you. And obviously, if you open your test, you know who contributed to that statistic. So why no plus c? Well, it will be f of b plus c minus f of a plus c. When you remove the parentheses, it's f of b plus c minus f of a minus c. When you distribute the minus, and then they die. And you just have this. So that's why there's no plus c. Technically, is there plus c? Yeah, there is, right? But it cancels, so we don't write it. The same thing like when you do the implicit differentiation and you're not putting dx over dx every time you differentiate things, right? We didn't talk about it even until I mentioned it all the way pretty much at the end of the chapter 3 that, oh yeah, by the way, I took the derivative of x in respect to x, so, but it cancels, so I don't write it. Great. What is the integral? So let's go do some examples. Integral of, let's go from 2 to 6 of 4 over x dx. The magic trick? So what's the integral over here? What's the antiderivative? 4 ln. Yes, say it. Absolute value of x. It's not there for decoration. We talked about it. It was -1 on the test. Now people are self-identifying themselves, I see. 4 ln absolute x computed from 2 to 6. Because 4 gets kicked out in front of the integral. It's a constant. And you have integral of 1 over x. So 4 is kicked out. Integral of 1 over x is ln absolute x. So now, we have 4, and in parentheses, ln 6 minus ln 2. Now, I don't have to put absolute values anymore because I have positive 6 and I have positive 2. Right? I could have had over there like -7 to -3, and this would still work. All right? So, yeah. What I can't have, guys, is -2 to 6. I can't have -2 to 6 because -2 to 6 goes through 0, and 0 has a vertical asymptote, and that's where the explosions happen for Calc 2. So, yeah. But I could have two negative numbers, and ln would still work because of absolute values. You must have those absolute values there. So now, when I do this, oh, we can use the formula. That's 4 ln 3. Right? Because subtraction of ln's goes in a division of the arguments. So 6 divided by 2 is 3. And if you really want to be cute, you can bring the 4 inside, and 3 to the 4 is 81, so it's ln 81. I mean, that's if you want to be as awesome as I am, obviously. Or you can just totally skip over that and not worry about it. So the answer that I would give is ln 81. And then that's just one punch in a calculator, rather than 4 times ln of 3. The next problem, say 0 to... See, this is what I want to go now back to our previous lecture and see what we used to do here. It was 2 to 6. Okay, not all limits are 2 to 6, okay? But I want the exact number so we can compare it to our calculations from yesterday, right? Yesterday we had those calculations that gave us 7.3 and 8.3 as bounds and said that the area is in between. So let's calculate the exact area quickly. Yeah, Calc 2 class in the future. I'm looking for a decimal answer. That will tell me. I'm looking for a decimal answer, 1 or 2 decimal precision. Let's go 2. All right, let's go 2 decimals. I'm looking for a decimal answer because I want to compare it to yesterday's 7.3 to 8.3. And then remember we improved it to 8.1. So the number that you are getting now better be between 7.3 and 8.1. So I'm looking for decimals this time around. I'm going to actually work on this problem now, and then you guys, so this is going to be x to the 1/2 dx from 2 to 6, which is x to the 3/2 over 3. And then when I say halves, I put it right up in the numerator, because the double fraction will do that. Computed from 2 to 6. This is equal to 2/3 6 to the 3/2 minus 2 to the 3/2. When you are using your calculator, just use 1.5 as the exponent, right? Because that's what 3/2 is. So let's go. Oh my God, man! Can you please tell your comment from California to stop playing? Look at you.
That's great. It's like, okay. Yeah. That's enough.
Call all of them and tell them to stop. Just quit. That's what I asked. Like, are you from Serbia? Do you know? Because, Ryan was like, yeah, there's like 7.5 million back over there, and then about 6 million over here. Like, out of 13 million, I was exactly that person that you met like 13 years ago in Colorado. So 600,000 in Chicago. Good. Yeah. All of the hotels, all of the transportation and trucks and stuff like that. Yeah. Pretty much everything underground. And then I think 350,000 in Cleveland. So that's about $1 million.
I'm going to take Cleveland.
Yeah. It's about $1 million just in those two. Now with the latest trains and the highway and all right, so what do you have? We have 2/3 times 6 caret 1.5 minus 2 caret 1.5 will give us 7.91. Yesterday we said that it was 7.3 less equal than area less equal than 8.1 when we did the nicer, right, the finer grid, right? We doubled the amount of rectangles. So now we see 7.1 is exact. Well, it's not exact because we cut off the integer or the number, but we see it is in between. That's that. If you can integrate from 4.9, then you better be able to compute two numbers in whatever answer you get. And it's top minus the bottom. If you're looking for the area, make sure that the function is not dipping below x-axis. And if it does, your job is to cut there, bring that one up with the absolute value, and then find the overall area. You have to be careful. If the question is calling for the value of the integral, you just plow through it. Don't worry about cutting and checking and all that kind of stuff. But if it's asking for area, you have to stop and you have to compute, make sure that all of the parts are above x-axis, and you'll be fine. That's that. So we'll be back in a few minutes with the fundamental theorem of calculus. If I had the tan, that would be, yeah, but I don't.